Ladies and gentlemen, we're concluding chapter 17 today. And I started doing an activity without the video, and a student kindly reminded me. I want to thank her. Thank you. And we have this reaction here, and it's called Beta Decarboxylation. Her name is still showing a little bit. I redacted her. Okay. You okay with that? Yeah. I can start the video over if you want. Okay. All right. Beta decarboxylation. Now we have to understand what that means. If you have a carboxylic acid that is beta to any carbonyl, then it is a candidate for beta decarboxylation. So let's verify that those three circled carboxylic acids are indeed beta to a carbonyl. Okay? So I'm going to start with the carbonyl that's closest, and you're going to remind me what alpha means. Here's a carbonyl. Where's alpha? Right, so you don't say right there. Help me out. The right next to it on the left? Yeah. So that's alpha, which means the carbonyl, which is one more carbon away, is beta, which means it's a candidate for? Nice, beta decarboxylation. Let's do it again in pink. Here is a carboxylic acid circled down here. Where's the closest carbonyl? Right here. Where's alpha to this carbonyl? Next door. I'm putting it in pink. And I broke beta. It's alpha is next door, and beta. Hey, that's also a candidate for beta decarboxylation, isn't it? And then we'll go with green. Oh, no, baby blue. Here is another carboxylic acid. Is it beta to a carbonyl? The answer is yes, because there's the carbonyl. There's alpha to the carbonyl. There's beta. It's the candidate. And I do want to save some time by not doing, do the entire mechanism for one, and then move on to the next one, and then move on to the next one. But I'm going to use colors again, but I'm going to say, do the whole red mechanism, and then proceed with the blue mechanism, then proceed with the green. Or I guess I'm going red, pink, blue. So I'm just going to write it this way. Red, pink, and blue are three separate mechanisms. The order will not be graded. How's that? Okay. Red, pink, blue are three separate reactions. She doesn't like that blue? Okay. We're going to go green. Ooh. Well, look at that. I bet you can see the blue now, but you won't be able to see it when I do the mechanism. Okay, I hear you. All right, green are three separate mechanisms. And at this level of organic chemistry, I'm not going to test you on which one should go first, okay? That's all I'm saying. You will not be graded on order. Normally you are graded on the order. And I think this is really going to help you learn this mechanism, because you're going to see the same thing. Step one in red, step one in pink, step one in green. They're always the same. The carbonyl breaks and grabs the H. Sigma between the O and the H breaks and becomes a carbonyl. I want this to be nice and big. There we go. And then the third step is that. Those arrows look familiar? Maybe not. And do the same thing in blue. Pink. Pi bond breaks, and where does it go? You tell me where this arrow has to end. I started it, and I kind of gave a hint with which direction I went in, but goes to the H on the beta carboxylic acid, right? What happens to the sigma between the O and the H? Becomes a carbonyl pi, correct? And yeah, what happens to this sigma bond here? Where's it go? You got to resonate towards that first arrow, right? Based on, here was your first arrow this time. And the order doesn't matter. If you memorize it with the order wrong, you're going to be fine. Okay, whatever it takes. And what I want you to be thinking of is like, this looks like the resonance that benzene's doing all the time. That's a special thing. What do I mean by that? I'm just going to bring it up because a lot of reactions, their foundation is on the electronics of this type of electron flow. Doesn't that look very similar to what we did? Let me make it even clearer with arrows. And that's benzene resonance. It's not a reaction, but it's a very, can I just summarize it this way because we haven't done anything with benzene yet? It's a very favorable electron energy situation with that number of pi electrons moving around. 6 is a nice number. And when you're done, you just got your 2 resonance forms of benzene, right? That's an aside. And we're going to do the same thing in green. Carbonyl, grab H. Resonate. Resonate. Okay. And the intermediate, only one intermediate, would be 3 intermediates. You should do red first, then do pink first, the second, and then do green, or whatever order you decide. You're really supposed to finish the mechanism, then do the next one. Okay? And let's just draw what we're supposed to get. In black, we'll make it a little bigger. We got a 6-membered ring, didn't change. There is a new pi here. What's on top here? What's on top? Look at the mechanism and tell me what I need to draw on there. OH. Okay, N is still NH. There's a double bond to this here. And it has an OH definitely to the right and down. Oops. And what about over here? What happened to this O? What happened to this O? OH. And down here we have a no carbonyl, but we have a double bond here and an OH. What do you call these functional groups that are here that will not be here when we're done? Every one of them is the same. The new functional groups you made all have the same name. What are they? Enol. 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 En. You want to be a little more accurate? How many double bonds? Sorry, how many alcohols? I don't know. En is en diol. Same idea though. The only reason it's a diol is because there was already an OH there, right? And and you tell me the name of this reaction here in red. Oh, I shouldn't have drawn that last one in red. It's a green. Greenol. Okay. In red. This, if it could reach it, would grab an H And this would resonate. But it can't reach it. So what do I have to do to tell the instructor I know that you can't reach this H here in the same molecule? That's ring size 4. We don't have transition states normally with ring size 4. It has to be intermole. Nice job, guys. Intermole in purple. And it's that arrow that's the intermole arrow, isn't it? And keep doing it over and over, everybody. Pink, same story. That's the intermole in purple. In green, same story. Grabs H, resonate, intermole. And yeah, if you leave that intermole out, that's not good, right? Some of you tried on the test and you lost a point. It's a whole point because it's an important deal. And that gets us to the answer. Did you realize that was 6 steps? 2 in red, 2 in pink, 2 in green. And I'll just leave you with the other kind of question we ask on this. Okay, there's no we, Jazz, it's me. And we've got something like this. And you know me, your favorite box there. And I want to know how many of those carboxylic, oh yeah, here, good question too. Plus, and that's just stoichiometry right there. I want a number. And don't just count carboxylic acids and say they're all going to go away. What kind of carboxylic acids are candidates for beta decarboxylation? Beta to what? They have to be beta to a carbonyl. If they're not a candidate. So definitely, there's a carbonyl. This is alpha to the carbonyl. That's beta. That means bye-bye, correct? Once it's gone, let's talk about the carboxylic acid that's still one away from the carbonyl, because its story is also alpha, beta. You agree? It's a separate story, based on the same carbonyl though. Bye. What about this guy here? That's an ester, right? It has a carbonyl, right? It's not going to decarboxylate. This is all. Do I have to say it has to be a carboxylic acid or else you can't decarboxylate? I should have said it a long time ago. Only for carboxylic acids that are beta to a carbonyl. But this is the carbonyl of the ester, correct? So in purple, this would be alpha, beta, bye-bye. I should have had another copy of that molecule, huh? I think it's still clear. It's a video too. I don't think we're losing anything on the right side, are we? This is a carbonyl. This is alpha. This is beta. The carboxylic acid is not that carbon. No reaction. Same story, backwards thinking. This is a carbonyl. There's alpha. Beta is not a carboxylic acid. No reaction. So we're going to copy everything except for the X's, and because we're using stick figures, you don't have to show these H's, do you? No. So what we have is in blue, we have our ester survived because it always will. CH2 once, twice, carbonyl, ketone will always survive. CH2 once, twice, 3, and CO2H. I drew it a little nicer this time. There's no change on the right side. And how many CO2H's did I lose? CO2s really, okay, 3. It's not always going to be 3, okay? And that's the end of that video. I hope it was educational.